Hi, John Golden here. We're looking at first section of our text, Active Calculus, um, and our first chapter, Understanding the Derivative. And we start off this question, how do we measure velocity? Okay, so velocity you're probably familiar with as a vocabulary word. Um, Um, so how this, looking at the text, how it usually starts is kind of with these motivating questions. So we're trying to think about each of those. Um, and here it's got kind of this big picture. Calculus can be viewed broadly as the study of change, right? So what is the rate of change of some quantity we're studying? That's kind of first question that we could start with there. Each section usually has a preview activity, right? So this preview activity 1.1.1, we're going to go ahead and do, and I'll use it as an excuse to model some Desmos too as well. Okay, so if you have open somewhere Desmos graphing calculator, desmos.com/calculator or desmos.com, and click from there. I'm logged in, right? So it gives me the opportunity to name and to save. I just called it Active Calculus 1.1 since that's where the section we're in. And the book is asking us to enter in this S of t here, right? And we could see even if, could we just paste that in? That didn't work so well, right? So let's undo that. But we could type it in. So S of t equals 64 minus 16 t minus 1 squared. Okay, so this is not a very illuminating graph, but in Desmos, just like on a graphing calculator, you can change your window. So I'm not really interested in going back too far or going forward too far. And since our function kind of goes up to 64, it's that 64 minus something, I'm just going to go ahead and put 70 for the window. And that gives us a pretty good idea of what's going on with this function. Okay, so what is the question asking? So construct a graph of the interval from 0 to 3. That's kind of how I chose my numbers. Label at least 6 distinct points on the graph, including the 3 points showing when the ball was released, when the ball reaches its highest point, and when the ball lands. Okay, so in Desmos, we can do that kind of by clicking on the graph. If we click on a point, it'll kind of name it and label it there. Desmos also will kind of pre-select points that it thinks might be of interest, like an x-intercept or a peak here, right? So we can see those there. To click on other points, well, it's not going to let us just kind of pick. We could put in a value, right? So like at 0.5 seconds, what is the function? Okay, here it's on here, right? Because Desmos allows us to make sliders, we could even kind of give it a value, and then go up and let's change this to A and S of A, and then kind of label, just clicking the label will make that show. So now we can kind of move the point. We can change the kind of range on a slider. They said we'd be interested like from 0 to 3. We can change by how much it goes. We can even press play and kind of see what happens as it goes. It's just going back and forth. We can pick like always increasing, kind of just doing it one time. We can slow it down if that was going a little fast. All right, a lot of features. Okay, now, so what is this a graph of? And when we're reading that problem, it says that this function gives the height of the ball. It's very tempting when we look at this to think, oh, it's the path of the ball, like if we were looking from the side. And in fact, Galileo did figure out that projectiles go in pretty close to a parabola. So this is sort of what the path of the ball would look like if it's thrown out somewhere. But it's not. This is just a graph of height versus time. And it's actually a question we'll be thinking about, like why, since it's a graph of height versus time, does it still look like kind of the path of the ball? So that's something we definitely need to figure out. All right. Describe the behavior of the ball from 0 to 1 and from 1 to 3. Well, it looks to me like the ball's rising up until t is equal to 1 when it's at that height of 64, and then it's falling until it hits the ground. It started at 48 feet, so I'm not sure what's going on with that. It turns out that this is a pretty reasonable equation. Minus 16 is the acceleration in gravity in feet per second. So it's a pretty good model. It asks us to consider this expression, the s of 1 minus s of 0.5 divided by 1 minus 0.5. So you might notice that that looks like a slope computation, and it is, right? So if we have these 2 points, that would be the kind of the slope of the line between them. What does the value tell us about the motion of the ball? In particular, what are the units on this? So if s is in feet, and it doesn't really tell us what these are in the bottom, but we know our function is feet as a function of time, so it's time in seconds on the bottom, and that means that the units on this AV would be feet per second. Now this is just a preview activity. It's trying to get you thinking about the ideas that we're going to have. All right, so let me stop that animation. And we wanted s of 1 minus s of 0.5 divided by, the fraction's only on the 1, right? I've got to put it in a group to get it to divide the whole thing. And then I could type out 1 minus 0.5, or I could just figure it out, right? So it's 8. So what is 8? The slope from 0.5 so from that point up until this point, the slope is 8. Right? So if I connected these two with a line, it doesn't look like 8. It looks less steep, but we changed the window, right? So these are going up by 2, and this is how far it is in 1. So if I draw this line, it goes up 4.5 a unit, so it would go up 8 in a whole unit. Okay, so the slope is 8 feet per second, and we're going to see more about what that means. So we read through. The book has some really nice features, right? If it asks you kind of to refer back to something, you can click on it and it'll pop a little image of what that was. Here it makes this definition that, yes, what we're looking at is average velocity. The ball was at, what was it at? 60 feet, and then it was at 64 feet. So what is the average rate of change between those two? 8 feet per second. Now it asks us, boy, for a whole bunch of different average velocities. Right, so well, we could set up our function here to use, well, why don't we have 2 points. And we can make this one go from between 0 and 3 as well. And then we could turn this into we could even give this a name if we wanted to have it have a name. Desmos won't let us type like a 2-letter name, right? So, but if you use the subscript, which is like the underscore, we could call it a sub v equals there. All right, and then we can change these two. So when it asks us to figure out 0.4 to 0.8. And we actually don't have to move the cursor, move the slider. We could just type in the value we want there. Oh, interesting. So from 0.4 to 0.8, it's increasing even faster than it was up here at the top, where it was only going 8 feet per second. This average change is 12.8 feet per second. So we could go through and figure out these. Boy, it asks us to get down to a really tiny difference, right? Between 799 thousandths and 8/10. So will this still do that? So this is kind of at the A, and by the time we get to B, it's only 6 feet per second. So it's kind of slowing down. So what this is asking us to do is to collect a lot of data from 0.8 to 1.2, 0.8 to 0.9, 0.8 to 0.81, 0.801. So figure out all of these. On the graph, sketch the line that passes through those 2 points. Right? So it gives us that. If we wanted to draw that line in Desmos, we'd have to know something about kind of the equation of a line. We have a point, we have a slope. So if we want to make it go kind of through those lines, we could maybe use point slope line to figure that out. But here we're really just asking us to kind of sketch, to draw, to think about that. Use a graphing utility to plot it. Well, we've already done that because that's just a way that makes sense to work. Zoom in to the graph. Okay, well, we can do that. So as we zoom into the graph, we're wondering about when A is 0.8. Right, so if we zoom into the graph here, the zoom in is just the plus. Desmos kind of zooms to the center of the window. Okay. Now it looks just like a line. Right? So as we move it though, you can see we've really zoomed in. This is only 1,000th of a second difference here. But if we were looking at 1,000th of a second, this looks almost just like a line. Right? And I can maybe undo to get back to our window from before. So here it's trying to change us from this idea of average velocity to could we say, kind of at this moment, what is the velocity of the ball? Okay, so I'm going to leave it for you to think about those questions. As we read on, there's more activities also including this function. So when I assign reading from the text, what I really mean is kind of try these problems. Math is ultimately about doing, right? It's not a collection of facts, it's can you do it, right? So in your notes, you can have a paper notebook, you could be jotting down kind of answers to these sorts of things on your homework Google Doc. You could use screenshots of the Desmos in there if that helps make sense of that. But somehow be keeping track of your work as you go through. It has, the text has examples. They expand out when you click on things. And then each section will end with a summary where it tries to kind of tie the ideas back. Dr. Bolkins, who is a professor at Grand Valley, has done, and the people who've collaborated with him on the book have done a lot of work to try to make this readable for a math book. So give it a go, try to make sense. Ask questions. You can ask questions to me on the course document. You can ask questions by email. You can ask questions in a meeting, right? By far, right, one of the worst things about asynchronous learning is there's not the easy place to ask questions that it'd be like if we were face-to-face in class and I was started off class asking, all right, are there any questions? And you could ask about things from the book or exercises you were trying. Every section ends with exercises. If you look at the work for today, I ask you to try kind of 4 of these first 6. These first 6 problems, the first several problems in a section, have the answers. And then there will be a couple problems kind of left for you to work on your own. And then if you look at our assignment page for this, it asks you to do problem 6 and then to try problem 7 or problem 8, your choice. Okay? And you'll be kind of submitting some of your work for those in a Desmos activity, which is where I'll be able to see kind of, what are you doing with this sort of stuff. And you can submit it in the Desmos activity. There will be places for you to type in, or there'll be a place for you can upload a picture. So we'll do probably a separate video that shows kind of how that works with the Desmos activity. All right. But that's a bit of an introduction to the book, how the book works, a bit of an introduction to the Desmos calculator. If you go to learn.desmos.com, there's lots of things about how to use different features on the calculator. It's quite a powerful tool, way better than any handheld graphing calculator has ever been, and getting better pretty rapidly as well. All right, so but that's it for this first video. Hope it was intelligible. You can give me feedback on the videos, what would make them better as well. All right, so thanks very much.